Hello and welcome to a first video in a series about automatic theorem proving in Pecan. This time we're going to talk about magic squares. So we'll start by talking about what magic squares are. Magic square is a grid of numbers where every row, column, and diagonal adds up to be the same number. So, for example, the one on the screen, we have 2 plus 6, 7 plus 6 is 15. The first column we have 2 plus 9 plus 4 is 15, and the first diagonal from left to bottom right is 2 plus 5 plus 8 is 15. So you can make these with other sizes, but we're going to focus on 2 by 2 and 3 by 3 because those are the easiest to understand. So let's switch to writing some Pecan code. Okay, so now we can start writing some Pecan code. So the first thing we're going to do is define what magic square is. And for the first little bit, we're just going to focus on a 2 by 2 magic square, which in fact does not exist. And we can prove this using Pecan. So first we need to define what we mean by a 2 by 2 magic square. So we're going to define some variables a, b, c, d, and sum, which are all natural numbers. So now let's define what it means for a, b, c, and d to be a 2 by 2 magic square. So a, b, c, d is a 2 by 2 magic square with some sum when the rows add up to be sum and the columns add up to be sum. And the two diagonals also add up to be sum. So first, let's do the rows. So a plus b equals sum, and c plus d equals sum. Those are the two rows. Now let's do the columns. A plus c equals sum, and b plus d equals sum. And finally, we'll do the diagonals. A plus d equals sum, and b plus c equals sum. So this defines almost what it means to be a magic square. The other important restriction is that the a, b, c, and d have to be distinct, because otherwise we could just use 0, 0, 0, 0, 0, and we get a magic square of 2 by 2 by 2. But that's incredibly boring, so we're not going to do that. Instead, we're going to say that all the numbers have to be distinct. Sometimes people will say the numbers have to be between all 1 to 4, or 0 to 3, or all less than 4 or something, but that's not a restriction that we're going to make because there's no magic squares that are 2 by 2, regardless of how you choose your numbers. And we can prove that using Pecan. So let's prove that now. So first, we'll write prove that, and then inside the curly brackets we can write our proposition that says there are no 2 by 2 magic squares. So prove that there does not exist a, b, c, d, and sum such that a, b, c, d, sum is a magic square. Let me move this a little bit. Okay, so there does not exist a, b, c, and d such that a, b, c, and d are a magic square that's 2 by 2 with some sum. So now we can use Pecan and run this, and it says success, meaning that there is no 2 by 2 magic square using any natural numbers as long as there's 4 distinct natural numbers. So that's interesting. However, this doesn't mean that Pecan is a general purpose constraint solver. It's not suitable for all tasks, but it is a theorem prover. So a lot of constraint solving systems, like the ones in Prolog, for example, will not be able to tell you that there is no solution to this unless you give them a bound on the numbers. But Pecan can prove that there are no solutions. Okay, so now let's talk about 3 by 3 magic squares. Because as we saw earlier, 3 by 3 magic squares do exist. So we can use Pecan to find them, we can use Pecan to prove that there are infinitely many of them, and we can use Pecan to prove exactly which numbers can be the magic sum of a magic square that is 3 by 3. So again, we're going to start by declaring some variables, a, b, c, d, e, f, g, h, and I, and some that are all natural numbers. These are going to be the numbers in the grid, and of course the magic sum. Now write a predicate called magic sum, or magic square, sorry, that says when these numbers are a magic square with this sum. Will be exactly like before, except with more numbers, of course. So first the rows, a plus b plus c equals sum, d plus e plus f equals sum, and g plus h plus I equals sum, and the columns, a plus d plus g equals sum, b plus e plus h equals sum, and c plus f plus I equals sum. And finally the diagonals. Okay, now we just need the constraint that everything is distinct, and this is a definition of a magic square in Pecan that will work. However, There's a more efficient way to write this. You could use some built-ins to do that more efficiently, but we won't do that because this is actually, I think, a clearer way to write it when we're only talking about a 303 magic square. We're going to do two additional things that make this run a little bit faster. We're going to say that sum is a natural number. This will constrain the search space a little bit. And then we're going to tell Pecan to post-process this section here, which basically says simplify the automaton that represents this predicate. So now we can use Pecan to find magic squares. So we can say, give us an example using nat format, because these are nats. This is just an output formatting thing. You don't have to use nat format. Of a magic square, A, B, C, D, E, F, G, H, I, and sum. So we can now run our program. It's going to take a second because this is a more complicated predicate than the previous one, but it will tell us a value for every one of the numbers in the square and for the magic sum itself. So here we can see sum is 15, I is 6, H is 8, G is 1, F is 0, E is 5, and so on. A lot of the times, people don't allow 0 to be one of the numbers in a magic square, but we will because it doesn't actually cause any problems. And there's no good reason to not allow 0. After all, 0 is a natural number. So we can now find magic squares, but what we're really interested in doing is proving good magic squares, because any program that is worth its salt can find magic squares. But a theorem prover can prove things about magic squares. So now we're going to prove that there are infinitely many magic squares. So the first thing we're going to define is what a magic sum is. So sum is a magic sum when there exists A, B, C, D, E, F, G, H, I, such that A, B, C, D, E, F, G, H, I is a magic square with some sum. Because for the moment, we only care about the sums, we don't care about the numbers in the grid, so we're just going to get rid of those, not worry about it. So we're going to prove that there are infinitely many magic squares, which it's enough to show that there are infinitely many different sums that can be the sum of a magic square. Again, as I said earlier, a lot of people will like to constrain these numbers so that they're all, 1 to 15 or 1 to 9 or whatever. But doing so means that it's not as interesting a problem because you lose a lot of solutions. So we're going to focus on the case where just any natural number is allowed. So we're going to say theorem, there are infinitely many 3x3 magic squares. And to do this, we're going to say for all n, which is a natural number, there exists a sum that is bigger than n and is a magic sum. So this says that, there's a magic square with a sum bigger than 0, there's one with a sum bigger than 1, there's one with a sum bigger than 1,000, there's one with a sum bigger than 10 million, and as high as you want, there's always more magic squares. So Pecan can prove this fairly easily, and we will say one more theorem, which is that the only sums possible are 3n, where 3n is at least 12. So all the sums of magic squares are multiples of 3, and they're all at least 12. So we'll say for all sum, if sum is greater than or equal to 12 and is a multiple of 3, such as sum is 3 times n, if and only if, that's what this little double arrow thing means, if and only if it is a magic sum. So we can prove that using Pecan 2, and let's do that now. So again, it's going to take a second. It has to rebuild the automata because we didn't save it. You can save the automata to a file, and then it will be much faster every time you run it because you won't have to regenerate the automaton every single time. But this is fine. It's not too slow. So first we prove there are infinitely many 3x3 magic squares, and we prove that the only sums possible are 3n, where 3n is at least 12. Okay, so thanks for watching. We'll talk about more stuff next time.